This video for required practical 5 for chemistry, rates of reaction. You are going to need two chemicals for the first part of this practical, and they are hydrochloric acid at 1 molar and sodium thiosulfate solution. Now when these two solutions react, they will make what's called a precipitate, which is a solid made from two liquids. Now that solid is going to make the solution go cloudy, and eventually it will make it so cloudy that you cannot see through it, which is the basis of this practical. Now, one of the side effects of this is it also creates sulfur dioxide gas, which can irritate the lungs of people with asthma, so we need to try and prevent too much of that gas being produced. So when you're clearing out your bottles, make sure you pour them into a stop bath. First thing we have to do is make up our different concentrations of sodium thiosulfate solution. Your most concentrated one will just be neat sodium thiosulfate. So I'm just going to fill up 50 centimetres cubed in my measuring cylinder. And that will go straight into my measuring cylinder, into my conical flask. That's my 40 grams per decimetre cubed sample. The second sample you need to make up is an 8 gram per decimetre cubed sample. Now to do that, you're going to put 10 centimetres cubed of your sodium thiosulfate into your measuring cylinder. And then you are going to top the rest of the way up to 50 using distilled water. This is going to take some time, so I'm going to cut there. Okay, now we're getting to the final stages of this experiment. Remembering that in an experiment like this, the only thing we want to be changing is the concentration of sodium thiosulfate. So the concentration of our hydrochloric acid will always be 1 molar, and we are always going to use the same volume, which is 10 centimetres cubed, which I've pre-measured here. Also remember that the room temperature and the temperature of our chemicals should all be the same as well, because temperature will have an impact on rate of reaction. So what I'm going to do now is start both of these off so you can see the difference between them. You're going to do one at a time. So I'm going to pour them in, start my timer, I'm going to give them a little swirl, and then if you film directly from above, we should start to see the solutions going cloudy, and eventually the solutions will be so cloudy that it will start to obscure the cross. So this one, our higher concentration, you could already start to see a clouding. This one has done very little so far. So you can see the enormous difference in rate of reaction. This one, I can no longer see the cross, so I would stop and record how long that was. This one, you can see, again, there's been very little change so far. So this one I would take away and pour into my stop bath to prevent excess production of sulfur dioxide gas. This one I'd have to leave until I can no longer see that cross inside. Welcome to the second part of this video, which is all about the alternative method of researching the rate of a reaction. So this time we're going to be changing the concentration of our hydrochloric acid. So I've got a 1 molar sample and a 2 molar sample. Again, to make sure that this is a fair test, we are only changing the concentrations of the acids. We'll be keeping the volumes, the temperatures exactly the same. The other thing we're going to be adding to this experiment is a magnesium ribbon. These have been pre-measured to 3 centimetre lengths, but when you're writing about this experiment, you could choose to use a specific mass, but length is equally good, and it also helps to regulate surface area as well, which is another thing that can affect the rate of a reaction. So this helps to kind of control both at the same time. Now what I'm going to do is collect the gas over water, it's called. So I'm going to start by taking a 100 centimetre cubed measuring cylinder, and I'm going to fill it with water by placing it into my water trough and slowly lowering it so that the water fills the container and there shouldn't be any air bubbles inside. So if I tilt that, you should be able to see there are no air bubbles. And as the gas is produced, as the hydrogen gas is produced from the reaction, we'll start to see the water being forced out, and we'll be able to measure the volume of gas we've produced. So I'm going to stand that upside down for a moment. We're going to be using a delivery tube to collect the gas and put it into that measuring cylinder. You've just got to be reasonably quick getting the bung into the top. Don't push it too far in, but you've got to make sure you've got a good seal. It's always worth testing that the bung and the measuring cylinder fit together nicely, because sometimes they can be a little bit different and it can ruin your experiment. So I've pre-measured 25 centimetres cubed of our 2 molar hydrochloric acid into the conical flask, and I'm going to have to add the metal strip and then start collecting the gas. I'm going to start my timer, and every 10 seconds I'm going to write down the volume of gas that I've collected. Now this can happen very, very quickly with your 2 molar acid, so do be prepared to work well as a team and work fast. You put your measuring cylinder over the end of your delivery tube, being careful not to push down, because if you push down you will pinch the tube and you will reduce the amount of gas, or sometimes even stop it altogether, which can cause the bung to pop off the top of your measuring cylinder. But you can see how quickly this reaction is occurring, and you can gather a nice set of data points showing how much gas you've collected after each 10-second time frame. This is just for comparison, so you can see the difference between the 2 concentrations. I've measured out 25 centimetres cubed of my 1 molar acid sample. If you're asked to do a risk assessment for this experiment, be aware that the magnesium metal is highly flammable, so it needs to be kept away from sources of ignition, and the hydrogen gas you produce is also highly flammable, so you do need to be very cautious that there are no naked flames around while you're doing this experiment. So here we go, just the same as before. You can already see a much slower rate of reaction. So these gas bubbles are produced much more slowly. So there you go, that's just for comparison. It will take a lot longer to make the same volume of gas, and this can be plotted on a graph that we will show you soon. Okay, so here is a set of results, and I wanted to talk through a few common mistakes that people make to ensure that you aren't somebody who makes them. So I've got my 3 trials and I've calculated my means. Now I've made my first error here, because whenever you're calculating a mean, you add up the number of results that you've got, so in this case 3, so I'm going to add all of those up, and then divide by how many results there were. So I'm going to add all of these together and divide by 3. Now this will often give you a big long decimal. Now what you are not supposed to do is what I've done here, which is include lots of decimal places, because my initial measurements were not measured to 2 decimal places, so I should not include them. What I should have done is use those decimal places to round up to make it 173 instead of doing 172.66. The second error, which I have not made on this line, is if you have an anomaly in your results, you are not supposed to include it in your mean. So the 120 result I'm going to exclude. I'm just going to do 74 plus 80, and now I only have 2 results, so I'm going to divide it by 2, which will give me a mean of 77. Okay, here is the graph I've plotted of my results. I've got my axes labelled, so I've got my units clearly marked on both, and I've made sure that my scale goes up evenly each time. Be very cautious of that, it's very easy to make a mistake there. I've plotted my results and I've got my line of best fit. So this is the correct way to create your graphs. Bear in mind, sometimes you get a straight line, sometimes you get a curve. Never do dot to dot. You always end up doing either a smooth curve or a straight line.